Every star you have ever seen in the night sky is burning. It is consuming itself, fusing atoms together in a furnace that has no equal on Earth, generating so much energy that you can feel it from 93 million miles away as warmth on your skin. But that burning cannot last forever. The fuel runs out, the pressure fails, and when it does, what happens next is among the most violent, most bizarre, and in some cases most beautiful events the universe can produce. We tend to think of stars as permanent fixtures. The same constellations our ancestors drew pictures inside of are the same ones we look up at tonight. That sense of permanence is an illusion, though. Not because the stars are changing on human timescales, but because what we call a star is just one phase in a much longer story. Before a star, there was a collapsing cloud of gas and dust. And after a star, there is something else. Something that can be stranger and more extreme than the star itself ever was. The universe is full of dead stars. Our galaxy alone contains hundreds of billions of them, drifting silently through space, collapsed into states of matter so extreme that nothing on Earth comes close to describing them. Some of these remnants are dense enough that a teaspoon of their material would weigh 1 billion tons. Some of them are spinning so fast that their surfaces are moving at a substantial fraction of the speed of light. Some of them have magnetic fields so powerful that if one were ever to pass within the distance from here to the moon, the iron in your blood would be ripped free from your body before you felt anything else. And some of them have collapsed so completely that even light cannot escape, bending space itself into a one-way trap that nothing, under any known physics, can ever leave. To understand the dead stars of the cosmos, you first need to understand that not all stars die the same way. The kind of corpse a star leaves behind depends almost entirely on how massive it was while it was alive. Mass is the single variable that shapes every aspect of a star's life and, crucially, its death. Think of it as a dial. Turn it up and you compress billions of years of slower stellar evolution into a faster, more violent trajectory that ends in something much more extreme. Stars like our Sun, and the vast majority of stars in the galaxy are in this middle range or smaller, spend their lives fusing hydrogen into helium in their cores. That process generates an outward pressure that holds the star up against gravity. The Sun has been doing this for about 4.6 billion years and has roughly 5 billion more years to go. But when the hydrogen in the core is finally exhausted, the core contracts under its own gravity, and the outer layers of the star expand enormously, turning the Sun into a red giant. In that phase, our Sun will swell to roughly 200 times its current size, large enough that it may engulf Mercury and Venus, and possibly Earth. Eventually, even the helium in the core burns out, and the red giant can no longer sustain fusion. At that point, the outer layers drift away into space in a slow, expanding cloud of gas called a planetary nebula. A glowing shell of expelled material illuminated by the hot core left at its center. What that core becomes is a white dwarf. For stars more massive than roughly 8 times the mass of the Sun, the ending is categorically different and vastly more violent. These stars can keep fusing heavier and heavier elements such as carbon, neon, oxygen, and silicon, each step burning faster than the one before it. When the core finally converts to iron, fusion stops entirely. Iron is the endpoint of stellar nuclear burning. You can fuse lighter elements to release energy, and you can split heavier ones to release energy, but iron is the bottom of the energy curve, and no reaction involving it produces a net gain. The core, no longer generating any outward pressure, collapses in less than a second. the outer layers fall inward, hit the incredibly dense collapsed core, and bounce outward in an explosion of almost incomprehensible violence, a supernova. What is left behind in the center is either a neutron star or, if the original star was massive enough, a black hole. So we have three destinations: white dwarfs for intermediate mass stars, neutron stars for stars of roughly 8 to 20 times the Sun's mass, and black holes for the most massive ones. These are not points on a spectrum so much as three fundamentally different categories of physics, each representing matter pushed into a regime that has no parallel anywhere else in the observable universe. We will visit each one in turn, from the most familiar to the most extreme. Imagine you are in a spacecraft, drifting toward a white dwarf. You are still millions of miles out, and to your instruments, it looks almost like any other dim, faint star. It glows in the ultraviolet and soft X-ray bands, which tells you it is extremely hot. Newly formed white dwarfs can reach surface temperatures of over 100,000 degrees Kelvin, easily outstripping anything our Sun produces. But it is tiny. The source of all that radiation is an object barely bigger than Earth. Everything that was once the core of a stellar system has been compressed into a sphere roughly 12,000 kilometers across. As you draw closer, the first strange thing you would notice is what the white dwarf is not. There is no fusion happening inside it, no nuclear reactions, no energy being generated. The light coming off it is not the product of burning anything. It is simply the residual heat from when the star was alive, slowly leaking out into space. A white dwarf is not a star in any active sense. It is an ember. It is the dense carbon and oxygen core of what used to be a star, supported against collapse not by the energy of nuclear fusion, but by a quantum mechanical property of electrons called degeneracy pressure. Electrons resist being compressed into the same quantum state, and in the extraordinarily dense interior of a white dwarf, that resistance is the only thing holding the object up. This is an important distinction from how the Sun supports itself. The Sun generates energy, and that energy creates an outward pressure that holds up the star against its own gravity. A white dwarf generates nothing. Its structural integrity is entirely a consequence of quantum mechanics, specifically the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state simultaneously. Pack enough electrons into a small enough volume, and this rule creates an effective pressure, even at temperatures near absolute zero. The electrons do not need to be hot to push back against gravity. They just need to be electrons. The matter inside a white dwarf is unlike anything you would encounter in everyday experience. Its density is roughly 1,000,000 times greater than water. A single cubic centimeter of white dwarf material, something the size of a sugar cube, weighs about a metric ton. The electrons in the interior are not bound to atoms. They roam freely through the compressed lattice of carbon and oxygen nuclei in what physicists call a degenerate plasma. This is one of the most exotic states of matter that actually exists in nature, and it has a property that strikes most people as deeply strange when they first encounter it. Unlike ordinary matter, it does not expand when it is heated. Heating a white dwarf does not make it bigger. The quantum mechanical pressure is already at its maximum. Temperature contributes only a small correction. A white dwarf is, in this sense, rigid in a way that ordinary matter is not. The cooling of a white dwarf is a slow, steady release of that original heat into space. Astronomers have measured it. A newly formed white dwarf glows at over 100,000 Kelvin. After 1 billion years of cooling, it drops to around 25,000 Kelvin, still extremely hot by any ordinary standard, but fading. After several billion years, it cools to temperatures where its surface glows white or yellowish white, in the same range as the surfaces of sun-like stars, even though it has no energy source. After 10 billion years, longer than our solar system has existed, a typical white dwarf is down to around 5,000 to 8,000 Kelvin, glowing dimly in the red and orange. The coolest white dwarfs ever detected have temperatures below 4,000 Kelvin, and they are estimated to be 11 or 12 billion years old, among the first stars that ever formed in the galaxy. And then there is the crystallization. As a white dwarf cools over billions of years, something remarkable happens in its interior. The temperature drops to the point where the carbon and oxygen nuclei begin to solidify, not into an ordinary crystal, but into a quantum mechanical lattice whose structure is unlike anything a chemist would recognize. The process begins at the center, where the density is highest, and works its way outward as the star continues to cool. The white dwarf, bit by bit, freezes from the inside out. Crystallized carbon, under the right conditions, is a diamond. The interior of a cooling white dwarf is, in a literal sense, turning into a diamond the size of Earth. In 2019, astronomers confirmed this using data from the Gaia Space Telescope, finding a distinctive pileup of white dwarfs at a specific temperature that could only be explained by the release of latent heat during this phase transition. The same way water releases heat as it freezes, slowing the cooling curve at the transition point. There are diamond planets scattered across our galaxy, but also diamond cores inside cooling dead stars, and the universe made them without any particular fanfare. The white dwarf BPM 37093 in the constellation Centaurus, about 50 light-years from Earth, is estimated to be a crystallized carbon body roughly the size of Earth and close to the mass of the Sun. Astronomers, with characteristic restraint, nicknamed it Lucy, after the Beatles' song about a diamond in the sky. The atmosphere of a white dwarf is perhaps the most chemically pure substance anywhere in the universe. Because of the extreme surface gravity, the lightest elements float to the top. Heavier atoms sink out of the photosphere in a matter of days to years, leaving a surface composed almost entirely of hydrogen or helium, stratified by weight. When astronomers observe spectral lines of heavier elements such as metals, silicon, and calcium in a white dwarf's atmosphere, they know the star has recently accreted material from nearby debris. About 25 to 30% of white dwarfs show these contaminating signatures. By examining what elements are present and in what proportions, astronomers can reconstruct the composition of the objects the white dwarf destroyed. Rocky planetesimals, disrupted moons, fragments of planets that survived their star's death and then eventually fell into the remnant core. The Hubble Space Telescope has found, in the atmospheres of two white dwarfs about 150 light-years away, spectral signatures consistent with the bulk composition of rocky planets similar to Earth's crust. Dead stars, it turns out, are eating their own planetary systems. Standing on the surface of a white dwarf, were such a thing physically possible, which it is not, would place you in a gravitational field roughly 300,000 times stronger than Earth's. A 70-kilogram person would weigh roughly 21 million kilograms. You would be immediately flattened. The object's gravity bends light measurably, redshifting the photons that escape from its surface as they fight against the gravitational pull. Even the stars behind it would appear slightly shifted in position. White dwarfs have a hard upper mass limit. A white dwarf cannot exceed about 1.4, 4 times the mass of the Sun. a threshold called the Chandrasekhar limit, named for the Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930. The calculation was remarkable for its time. Chandrasekhar was on a ship from India to England in 1930 when he worked it out, at 19 years old, by combining Einstein's special relativity with quantum mechanics in a way that no one had previously attempted. The scientific establishment, including the distinguished Arthur Eddington, initially rejected the result as absurd. It took decades for the limit to be accepted. Chandrasekhar eventually received the Nobel Prize in 1983, more than 50 years after the calculation. If a white dwarf in a binary star system accumulates enough mass from its companion, by pulling material from the neighboring star's outer layers, it can approach this limit. When it does, the degeneracy pressure can no longer hold. The white dwarf collapses catastrophically and then explodes in a particular kind of supernova called a Type 1a awakens. These explosions are so consistently bright that astronomers use them as standard candles to measure cosmic distances. And it was through this method that the accelerating expansion of the universe was discovered in 1998. Two teams of astronomers working independently with Type 1a supernovae at great distances found that the most distant ones were dimmer than they should be. They were farther away than the expected rate of cosmic expansion could account for. The universe was not merely expanding, it was expanding faster and faster over time, driven by a mysterious pressure now called dark energy. The tool that revealed this was a series of dead stars, exploding at the precise mass threshold that Chandrasekhar had calculated in 1930 on a ship crossing the Indian Ocean. The fate of the white dwarfs that do not explode is a slow, billion-year cooling toward darkness. After perhaps 10 trillion years, nearly 1,000 times the current age of the universe, a white dwarf will finally cool completely, ceasing to emit any light at all. It will become a black dwarf, a cold, crystalline, Earth-sized mass of compressed carbon drifting silently through space, invisible in every wavelength, its only trace being its gravitational pull on any object that passes too close. No black dwarf yet exists in this universe. The cosmos is not old enough. The coolest white dwarfs currently observable are still several thousand degrees. But in the far future, the galaxy will be full of these objects. Cold, invisible diamonds in the dark. The final physical remains of every star like our sun that has ever burned. Some theorists have speculated that given enough time, truly incomprehensible timescales, on the order of 10 to the power of 1,100 years, even black dwarfs will eventually explode, as quantum tunneling reactions accumulate at the centers of their cold, dense interiors and push them over the Chandrasekhar limit one final time. The dead would, impossibly, ignite once more. But that is so far in the future that the universe will have changed in ways we cannot currently predict, and it belongs more to the realm of mathematical speculation than observational science. Before we can approach a neutron star or a black hole, we need to witness how they are born. If you could somehow watch the final hours of a massive star from a safe distance, say, from a few light years away in a spacecraft with enough shielding, what you would see would be both terrible and spectacular in equal measure. The star has been fusing heavier and heavier elements for millions of years, each stage shorter than the last. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts centuries. Neon burning lasts about a year. Oxygen burning lasts about 6 months. Silicon burning, the final stage before iron, lasts just a few days. At the end of that process, the core of the star has become a ball of iron and nickel roughly the size of Earth, and it is surrounded by concentric shells of increasingly lighter elements, including silicon, oxygen, neon, carbon, helium, and hydrogen, each still burning in its respective shell. Then the silicon burning stops. There is no more energy to be had from fusion. The iron core, no longer supported by any outward pressure, goes into freefall. In less than a quarter of a second, something roughly the mass of the Sun and the size of Earth collapses to a ball about 20 kilometers across. The density during this collapse reaches extraordinary extremes. Electrons and protons are crushed together to form neutrons, releasing a flood of neutrinos. Incredibly light, nearly massless particles that interact with matter only weakly. So weakly, in fact, that the neutrinos from a stellar collapse will pass through the entire planet Earth as though it were not there. In a normal day, trillions of neutrinos from the Sun pass through your body every second and you feel nothing. But during a core collapse supernova, the neutron flux is so extreme and the density of the collapsing core so high that even neutrinos briefly interact with the surrounding material. The result is a shockwave of energy that travels outward through the star's layers. This shock, combined with a secondary boost from the staggering neutrino pressure, blows the star apart. The entire outer structure of the star, all that silicon, oxygen, neon, carbon, helium, hydrogen, is ejected into space at velocities of 10,000 kilometers per second or more. In a few hours, the star has gone from being a stable system to a glowing explosion visible across the galaxy. The neutrinos from the collapse arrive on Earth first, before the light, because they pass through the star's opaque outer layers at nearly the speed of light, while the light takes hours to actually break through the explosion. This is exactly what happened on February 23, 1987, when 3 separate neutrino observatories around the world detected a short burst of neutrinos, a total of 24 between them, just under 3 hours before astronomers first observed a brightening star in the Large Magellanic Cloud, a satellite galaxy 168,000 light-years away. That star was subsequently designated SN 1987A, and it remains the closest supernova observed by modern instruments. Its light arrived at Earth over 160,000 years after the star actually exploded, having traveled all that way before the detection. Scientists knew from those 24 neutrinos that a compact object had formed in the collapse, but for over 35 years, no one could see what the explosion had left behind. The debris was too thick and too hot. It was not until 2024 that the James Webb Space Telescope, in one of the first science observations it ever conducted, finally detected highly ionized argon and sulfur gas at the very center of the expanding remnant. The chemical signature of intense ultraviolet and X-ray radiation from a young neutron star, still buried inside the debris it was born in, finally confirming what those 24 neutrinos had hinted at nearly 4 decades before. You are now on a different flight path. The destination is a neutron star, and the experience of approaching one is in a different category from anything the white dwarf offered. While still far out, perhaps several 100,000 kilometers, your instruments start flagging the radiation environment. Neutron stars emit radio waves, X-rays, and sometimes gamma rays across the electromagnetic spectrum. The immediate vicinity of a neutron star is a hostile space. Not all neutron stars are the same in this regard, but even the quieter ones are radiating intensely in high-energy bands that would be lethal to any unshielded human being. The very young ones, still hot from the violence of their birth, glow at temperatures measured in tens of millions of degrees. Even older, cooler neutron stars maintain surface temperatures in the hundreds of thousands of degrees, because they have a deeper source of heat than mere residual thermal energy. The slow settling and rearrangement of their internal structure continues to release energy over millions of years. As you get closer, the gravitational effects become noticeable in ways that go beyond what a white dwarf produces. A typical neutron star packs between 1 and 2 solar masses, the mass of an entire star, or more, into an object roughly 20 kilometers across. That is roughly the diameter of a large city. The gravitational field at its surface is approximately 200 billion times stronger than Earth's. If you dropped a rock from a height of 1 meter above the surface of a neutron star, it would reach the ground moving at over 1,400 kilometers per second. The entire fall would take a fraction of a millisecond. Before it hit, the tidal forces, which are the difference in gravitational pull between the near side and the far side of the object, would have pulled it into a thin stream of subatomic particles. The escape velocity from the surface of a neutron star is roughly half the speed of light. This has practical consequences. Light escaping from the surface is measurably redshifted, losing energy as it climbs out of the gravitational well. The spectrum you observe from a distance is not the same as the spectrum being emitted at the surface. And the space-time curvature near a neutron star is extreme enough that the entire surface becomes visible from any single vantage point. The light from the far side of the star bends around the curvature of the neutron star's own space-time enough to reach a viewer positioned at the front. You would see more than a hemisphere. You would see the entire surface simultaneously, wrapped by gravity into your field of view. The surface itself defies easy description. It is covered by a crust composed primarily of iron atoms at its outermost layer. But this is iron under conditions that do not exist in any laboratory on Earth. The gravity has compressed the atomic structure until the normal rules of chemistry have broken down. The surface layer is perhaps a meter thick, and at these pressures, the iron lattice forms a rigid, solid structure that is in some respects harder and more rigid than any material known. Estimates suggest the neutron star crust can withstand shear forces about 10 billion times greater than the strongest steel. Just below the outer iron layer, the electrons have been stripped from the atoms entirely, and beneath that, protons and electrons have been forced together to produce neutrons. A neutron star is essentially an atomic nucleus the size of a city. The matter in its interior is so compressed that each teaspoon of it would weigh roughly 1 billion tons. The thickness of the outer layers changes the character of the interior dramatically at each step. Just below the crust, there is a region where neutrons exist alongside the remaining atomic nuclei in what physicists call a neutron drip. The density is so high that neutrons literally drip out of the nuclear structures and exist as free particles alongside them. Deeper still, at densities far exceeding those inside ordinary atomic nuclei, the entire material becomes a sea of free neutrons, with a small percentage of protons and electrons. And then, in the inner core, the densities reach levels where no laboratory experiment and no theory can currently make reliable predictions. This innermost region may contain hyperons, particles heavier than protons and neutrons that are unstable under ordinary conditions, but might be stabilized by the extreme pressure. It may contain a superfluid of quarks. It may contain a phase called color-flavor locking, where quarks are bound into a structured lattice that has properties of both a superfluid and a superconductor simultaneously. No one knows for certain. Neutron stars are hiding the answer to one of the deepest open questions in nuclear physics behind 20 kilometers of compressed matter that no instrument has ever directly probed. At these densities, the normal theories of matter do not straightforwardly apply, and physicists are still debating what the interior of a neutron star actually looks like. One leading hypothesis suggests that, deep in the core, the pressure is high enough to free individual quarks, the fundamental particles that make up protons and neutrons, from their usual confinement, creating a state of matter called quark-gluon plasma that existed briefly in the universe just after the Big Bang and nowhere else since. This is one of the reasons neutron stars are considered the most extreme natural physics laboratories in the known universe. They may contain states of matter that cannot be created or sustained anywhere else. The information locked inside their structure could potentially discriminate between competing theories of the strong nuclear force at densities that no particle accelerator has ever achieved or is likely to achieve. The magnetic field is perhaps the most viscerally strange feature of the approach. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. To get a sense of that comparison, Earth's magnetic field is strong enough to align a compass needle. A fridge magnet is a few hundred times stronger. The strongest continuous magnetic field ever produced in a laboratory is about 45 Tesla, achieved using expensive, specialized equipment and a great deal of electrical power. A neutron star's field is on the order of 100 million Tesla at its surface. If such an object was somehow placed at the distance of the moon, it would pull the iron-rich hemoglobin straight out of your blood cells before you processed any other sensation. The field channels radiation into 2 tight beams from the magnetic poles. And if the magnetic axis is tilted relative to the spin axis, which it often is, these beams sweep around like a lighthouse as the star rotates. When one of those beams is aimed at Earth as it rotates, we detect a pulse of radiation with metronomic precision. These are pulsars, and they were first detected in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge, who was initially so baffled by the regularity of the signal that she and her supervisor briefly notated the source, LGM1, for little green men, before the correct explanation became clear. Pulsars spin with extraordinary speed. A young pulsar born in a supernova may rotate tens of times per second, and some pulsars have been accelerated by pulling material from a companion star, which adds angular momentum and spins them up to extraordinary rates. These are called millisecond pulsars, and the fastest confirmed one, designated PSRJ 1748-2446AD, sits in the globular cluster, Terzan 5, about 18,000 light-years away in the constellation Sagittarius. It rotates 716 times per second, nearly 43,000 revolutions per minute. Its equator is moving at roughly 24% of the speed of light. It is the fastest spinning solid object known to exist in the universe. If it were any larger, the material at its equator would be flung off into space. These recycled millisecond pulsars tick with such remarkable precision that they function as natural clocks, accurate enough to be used to test fundamental physics, to detect the faint wobbles in space that might indicate a passing gravitational wave, and to verify predictions made by general relativity to extraordinary precision. One of the odder phenomena associated with pulsars is something called a glitch, a sudden, tiny speed-up in the rotation rate that interrupts the otherwise perfectly steady slowdown that all pulsars experience as they radiate energy. Glitches are thought to result from the catastrophic transfer of angular momentum from a superfluid that exists in the inner crust of the neutron star to the rigid outer crust. The interior neutron fluid, being a quantum superfluid, can store angular momentum in quantized vortices. And when those vortices suddenly pin and then unpin from the crystal lattice of the crust, they transfer a burst of spin to the whole star. Glitches are, in this reading, a window into the quantum mechanical interior of a neutron star, observable by watching a pulsar tick slightly faster for a brief period. The physics of this is the same, in principle, as the physics of superfluid helium in a laboratory, just occurring inside an object more massive than the Sun. Among neutron stars, there is a special category so extreme that it deserves its own consideration. These are magnetars, a subclass of neutron stars with magnetic fields so powerful that they would strip the electronic structure from atoms at a distance, and that occasionally produce bursts of energy so intense that the comparison to any human-scale experience completely breaks down. A typical neutron star has a magnetic field on the order of 1 trillion times Earth's. A magnetar's field is another 1,000 times stronger still, reaching up to 100 trillion to a quadrillion times Earth's magnetic field, expressed in the scientific unit of Tesla as values between 100 million and 100 billion Tesla. The concept behind the term was proposed in 1992 by astrophysicists Robert Duncan and Christopher Thompson, who calculated that under certain conditions during neutron star formation, specifically when the newborn star is spinning fast enough and hot enough, a powerful internal dynamo could convert rotational and thermal energy into magnetic energy, amplifying the field to these extraordinary levels. The consequences of such a field are staggering. The magnetic energy density of a magnetar exceeds the mass energy density of ordinary matter. This means the magnetic field itself has enough energy per unit volume to distort the quantum vacuum. The seething foam of virtual particles that quantum mechanics tells us underlies all of space. Near a magnetar, the normally spherical shapes of atoms are deformed into elongated cylinders aligned with the field lines. Chemistry, as we understand it, would not function anywhere close to such an object. Molecules would not form in their normal configurations. The vacuum itself would behave differently than it does in empty space. Because the crust of a neutron star is physically locked into the magnetic field, any movement of the crust sends a disturbance rippling through the field. In a magnetar, these disturbances carry enormous energy. They produce starquakes, which are ruptures in the rigid crystalline crust, and when those occur, the magnetic field releases energy in the form of extremely powerful bursts of X-rays and gamma rays. On December 27, 2004, a magnetar designated SGR 1806-2 erupted in such an event, releasing in just 1/10 of a second more energy than our Sun emits over 100,000 years. Despite being about 50,000 light-years away, safely on the other side of the galaxy, the burst was energetic enough to measurably compress Earth's upper atmosphere and ionize the night side of the planet in the same way that only direct solar radiation normally does. Had this magnetar been located within a few thousand light-years, the consequences for life on Earth would have been severe. As it was, it delivered a flash of radiation that altered the chemistry of our upper atmosphere from halfway across the galaxy. The active life of a magnetar is short compared to other neutron stars. The extraordinary magnetic field decays over about 10,000 years, and as it does, the starquakes and X-ray bursts cease. What is left is an old, quiet neutron star that has lost its extreme magnetic field. Given how many supernovae have occurred in the Milky Way over its history, astronomers estimate there may be 30 million or more inactive former magnetars drifting silently through the galaxy. invisible to most forms of observation. Before we leave the realm of neutron stars entirely, there is one more event worth dwelling on, because it is among the most violent things that can happen in the universe, and because it is connected to a story about where the gold in your jewelry came from. Neutron stars can exist in binary systems, with pairs orbiting each other. Over time, the emission of gravitational waves, which are ripples in space-time predicted by Einstein's general relativity, causes the two stars to spiral inward. This is an extremely slow process over human timescales, but the universe is patient. As the orbit tightens over millions of years, the rate of gravitational wave emission increases, and the spiral accelerates. In the final seconds before the collision, the two neutron stars are orbiting each other hundreds of times per second, separated by just a few kilometers. The gravitational wave signal they emit in those final moments is a chirp, starting as a low rumble and rising rapidly in frequency and intensity. That can be detected in the distortions it produces in the length of precision laser beams on Earth. When the two neutron stars finally merge, the collision produces a short, intense burst of gamma rays, one of the most energetic events in the known universe, and releases a flash of gravitational waves, a chirp in the fabric of space-time itself. The merger creates a hypermassive object, unstable and doomed to collapse, that briefly outshines the combined light of all the stars in a billion galaxies. The jet of material launched along the rotation axis punches through the surrounding gas and, if aimed at Earth, appears as a short gamma ray burst, a phenomenon that had been observed for decades without clear explanation until a neutron star merger was finally confirmed as its source. On August 17, 2017, the LIGO and Virgo gravitational wave detectors simultaneously registered just such a signal, designated GWW 170817. The gravitational wave signal lasted roughly 100 seconds, far longer than the few seconds that merging black holes produce, because neutron stars are much less massive, and the final inspiral takes longer to complete. Just 1.7 seconds after the gravitational wave passed through Earth, a gamma ray burst triggered detectors on the Fermi and Integral spacecraft. Within hours, 70 observatories on every continent and in space turned toward the indicated region of sky, and they found the glowing remnant of the collision in a galaxy called NGC 4993, about 140 million light-years away. It was the first cosmic event ever confirmed simultaneously in both gravitational waves and light, and it became probably the most widely studied astronomical event in history. 84 scientific papers were published about it on the day of the announcement alone. The aftermath of the collision glowed brilliantly for the first few hours, then faded and reddened over the following days. That characteristic evolution, bright blue at first as lighter elements decayed, then fading to deep red as heavier elements took longer to decay, was the predicted signature of a kilonova, the name given to the radioactive fireball produced by a neutron star merger. The blue component came from lighter R-process elements, mostly strontium and other elements just heavier than iron. The red component came from the heaviest R-process products, lanthanides, elements in the range of lanthanum to lutetium, whose complex electronic structures make them highly opaque to certain wavelengths of light and give the kilonova its characteristic color signature. What those observations confirmed was something astrophysicists had long suspected but never directly witnessed. Neutron star mergers are the primary forge of the heaviest elements in the universe. During the collision, the environment of extreme neutron density and temperature enables a rapid nuclear reaction sequence called the R process. in which atomic nuclei absorb neutrons faster than they can decay, building up to masses that normal stellar fusion could never produce. The rate of neutron capture must be extraordinarily fast, millions of times faster than the typical radioactive decay timescale of the intermediate nuclei. And only a neutron star merger, with its near unlimited supply of free neutrons and its extreme thermodynamic conditions, can sustain the process. The elements created this way include platinum, uranium, iodine, and gold. The R process accounts for roughly half of all the elements heavier than iron that exist anywhere in the universe. The gold in a wedding ring, the platinum in a catalytic converter, the iodine in the human body. These atoms were forged in collisions like this one, distributed into the early universe's gas clouds, and eventually incorporated into the material that became our solar system. To put the scale of it plainly, every gram of gold on Earth was produced in a neutron star collision that occurred at least 4.5 billion years ago, somewhere in the Milky Way or its progenitor, and then travelled to the gas cloud that eventually became the Sun and its planets. The dead stars of the cosmos did not merely leave remnants behind, they built the chemistry of everything we are made of. The detection of GW170817 also provided the most direct confirmation yet that gravitational waves travel at exactly the speed of light. The gamma-ray burst arrived just 1.7 seconds after the gravitational wave signal, consistent with both travelling at the same speed across 140 million light-years, with the 1.7 second gap attributable to the physical processes that produce the gamma rays, rather than any difference in propagation speed. This single observation placed the tightest constraint ever on any potential difference between the speeds of gravity and light, ruling out entire classes of alternative theories of gravity that had predicted they should differ. The physics of the universe, in its most extreme settings, keeps passing every test we put to it. When the core of a collapsing star is massive enough, generally when the progenitor star was more than about 20 times the Sun's mass, the gravitational collapse does not stop at neutron star densities. The neutron degeneracy pressure that holds a neutron star up against gravity is itself overwhelmed, and the collapse continues. There is no known force in physics that can halt it. The core does not stop until it has compressed to a singularity. A point of theoretically infinite density, surrounded by a region of space-time so severely warped that even light, moving at 300,000 kilometers per second, cannot escape from it. This is a black hole. The boundary at which the escape velocity equals the speed of light is called the event horizon. It is not a physical surface in the way that the surface of a neutron star is a physical surface. There is no material there, no wall, no membrane you could touch. The event horizon is a mathematical boundary, a point of no return. Anything that crosses it, including matter, light, and information, can no longer escape, and from the perspective of the outside universe, can never be seen again. The concept had been anticipated mathematically almost immediately after Einstein published his general theory of relativity in 1915. Karl Schwarzschild produced the first mathematical description of what we now call a black hole just months later, while serving on the Eastern Front in World War I. Einstein himself was initially skeptical that such objects could actually exist in nature. A century later, we have direct images of two of them. We have recordings of the gravitational waves their mergers produce, and we can watch stars orbiting the supermassive one at the center of our own galaxy with a period measured in years. Stellar black holes, the kind formed in supernova collapses, typically contain between 5 and 50 times the Sun's mass, compressed into an event horizon radius of anywhere from about 15 to 150 kilometers. The Schwarzschild radius, as that boundary is called, scales simply with mass. Double the mass, and you double the radius. A black hole with the mass of our Sun would have an event horizon roughly 6 kilometers across. The Sun's mass squeezed into a ball the size of a city. You are now on final approach to a stellar mass black hole. Not the supermassive variety at the center of a galaxy. Those have event horizons spanning millions of kilometers and have their own distinct character. But a stellar remnant, the compressed corpse of a star that died in a supernova some millions of years ago. It is dark. It emits nothing by itself. You can only find it because of its effect on surrounding material and the gravitational lensing of background stars. Far out, the gravitational effects are subtle. The black hole bends light from stars behind it, creating arcs, rings, and multiple images of the same object. A phenomenon called gravitational lensing that Einstein also predicted, and which has since become one of the most powerful tools in observational astronomy. As you get closer, the distortion intensifies. Stars near the back of the sky appear to shift toward the hole, their light bent around its curvature. A perfect ring of light appears, an Einstein ring, formed by light from a directly aligned background source that has been bent around the entire perimeter of the event horizon. But it is not just background stars that bend. Light emitted from the accretion disk, full of material spiraling inward around the black hole, heated by friction and tidal forces to millions of degrees, wraps around the black hole in extraordinary ways. Light from the top of the disk bends around to become visible below it. Light from the bottom bends around to appear above. The inner edge of the disk glows with an intensity that no amount of distance can fully diminish, and the entire structure appears to fold and curve in a way that obeys the exact equations of general relativity that physicists have been using to describe gravity for over a century. There is a region called the photon sphere, at one point 5 times the event horizon radius, where photons travel in circular orbits. A photon at this radius is balanced exactly between escaping and falling in. If you could somehow place yourself in this region and look sideways, you would see the back of your own head. The tidal forces begin to build. A stellar mass black hole has its event horizon at a very small radius, which means the space-time curvature there is intense. The difference in gravitational pull between your head and your feet, or between the two ends of any extended object, grows rapidly as you fall inward. This differential stretching is called spaghettification, a term that is equal parts accurate and grimly playful. Your body, or any extended structure, is pulled in the direction of the hole more strongly at the near end than the far end, and simultaneously compressed from the sides as material is pulled toward the axis of the fall. The result is that the object becomes progressively longer and thinner, like taffy being pulled. For a stellar mass black hole, this process begins well outside the event horizon. You would be stretched beyond survival before ever crossing the boundary. For a sufficiently massive black hole, one containing millions or billions of solar masses, like the supermassive black holes at galactic centers, the tidal forces at the event horizon are actually mild enough that a human being could theoretically cross the horizon without immediately being destroyed. The stretching only becomes catastrophic far inside. This is one of the most counterintuitive things about black holes. Larger ones are less violent in their immediate vicinity. The supermassive black hole at the center of the Milky Way, Sagittarius A star, contains about 4.3 million solar masses. At its event horizon, roughly 12 million kilometers across, about a sixth of the distance from Earth to the Sun, the tidal force difference across a human body is about 0.02%. A falling astronaut would cross the horizon without noticing anything remarkable. The laws of physics would still seem locally normal. There would be no wall, no sensation of crossing a special boundary. The only thing that changes at the event horizon is the future. Once inside, every possible trajectory leads inward, moving, stopping, accelerating. Nothing changes the outcome. The singularity is not in front of you in space. In the warped geometry of a black hole interior, it is in your future in time. The laws of physics, as we understand them, provide no description of what actually happens there. From the outside, the story is dramatically different. An observer watching you fall into a black hole would see something strange. As you approach the horizon, the light you emit is increasingly gravitationally redshifted, its wavelengths stretched by the energy required to climb out of the gravitational well. Your image appears to redden and dim. Your apparent motion slows, frozen by the warping of time near the horizon. From the distant observer's perspective, you appear to approach the horizon asymptotically, never quite reaching it, your image fading into an invisibly dim and infinitely redshifted ghost. You do not, from their point of view, cross the event horizon in any finite observable time. But from your own perspective, you fell through in an ordinary finite amount of time. This is not a paradox. It is a genuine consequence of the way general relativity handles the relationship between different observers' measurements of time and space. The time dilation near a black hole is the same effect that GPS satellites must correct for, though far more extreme. The satellite's clocks run slightly faster compared to clocks on the ground, because they are higher in Earth's gravitational field and experiencing less gravitational time dilation. Near a black hole event horizon, time dilation becomes infinite. The observer outside sees the infalling observer's clock running slower and slower until it appears to stop entirely. If you could fall into a black hole while wearing a watch and transmitting a live feed, the people watching from far away would see your clock slow down, your movements slow, your signal redshift from visible light through infrared and into radio and then beyond detection, while you experienced nothing unusual at all. The accretion disk around an actively accreting black hole is one of the most energetic environments in the universe. Material spiraling inward converts a substantial fraction of its rest mass energy into radiation. The efficiency of this process for material orbiting near the innermost stable orbit of a black hole is roughly 10%. Nuclear fusion in stars converts less than 1% of hydrogen's mass into energy. The accretion process is 10 times more efficient than the most powerful energy source stars use. This is why accreting black holes, quasars, and active galactic nuclei are among the brightest objects in the observable universe, visible across billions of light years. A single stellar mass black hole accreting material from a companion star can produce as much X-ray luminosity as 10 billion suns. The interior of a black hole is the one place in the universe where our best theories of physics genuinely break down. General relativity predicts a singularity, a point of infinite density at which the equations cease to produce meaningful results. But physicists do not believe singularities are real in the final sense. What they believe, almost universally, is that the singularity is a signal that general relativity is incomplete, that at these extremes of curvature and density, a theory combining gravity with quantum mechanics is necessary, and that such a theory would replace the singularity with something finite and physically real whose nature we cannot currently describe. This is the frontier of theoretical physics, the search for a quantum theory of gravity that can tell us what actually happens inside a black hole. The black hole information paradox is perhaps the most profound open problem connected to this frontier. In classical general relativity, anything that falls into a black hole is irretrievably lost. Its information, in the physical sense, ceases to be accessible to the universe outside the horizon. But quantum mechanics contains a fundamental principle that information cannot be destroyed. This is not merely a statement about practical limits of measurement. It is a statement about the mathematical structure of quantum theory. If you have complete information about the quantum state of a system, in principle you can evolve it backward in time and recover all the information about what led to it. The destruction of information would break quantum mechanics at a fundamental level. Stephen Hawking proposed in 1974 that quantum effects near the event horizon cause black holes to emit thermal radiation, a slow, steady glow of particles produced by the interaction of quantum fields with the curvature of space-time at the horizon. This Hawking radiation carries no information about what fell in. If the black hole slowly evaporates away through this radiation, everything that fell into it, every particle, every piece of information, is apparently gone. Hawking spent the last decades of his life grappling with whether this information is actually destroyed, and before his death in 2018, he had softened his original position, suggesting that information might be preserved in subtle ways in the outgoing radiation, encoded in its correlations in ways that would be practically irretrievable but theoretically present. The question is still open. The resolution of the information paradox, when it comes, will require exactly the kind of quantum theory of gravity that physicists have been working toward for nearly a century. The time scale of Hawking evaporation is absurd in human terms. For a stellar mass black hole, the evaporation time is longer than the current age of the universe by a factor that exceeds a number with 67 zeros. In practice, any black hole formed from a stellar collapse will be absorbing radiation from the cosmic microwave background faster than it is losing mass to Hawking radiation for the entire foreseeable future of the universe. The evaporation of black holes is not something that will happen for an almost unimaginable length of time, but it will, eventually, happen. And when it does, the final seconds of a black hole's life are predicted to be a burst of highly energetic radiation as the remaining mass plunges down the Hawking spectrum and the whole evaporates completely. The dead stars of the cosmos are not distributed evenly. Understanding where they are and what they do to the environments around them fills in a broader picture of how the galaxy actually functions. White dwarfs are the most common type of stellar remnant. Roughly 97% of all stars in the galaxy are expected to eventually become white dwarfs, because the vast majority of stars are not massive enough to produce a supernova. The nearest white dwarf to Earth, Sirius B, orbits the bright star, Sirius, itself the brightest star in the night sky, at about 8.6 light-years distance. It was the first white dwarf ever discovered, inferred in 1844 by the astronomer Friedrich Bessel from a slight wobble in Sirius's proper motion, and later observed directly. It contains slightly more than the Sun's mass compressed into a sphere about the size of Earth. Neutron stars are far rarer. There are estimated to be around 1 billion in the Milky Way, compared to several hundred billion stars. But because they are small and often no longer emitting as pulsars, most of them are invisible. We can only directly observe the ones that happen to pulse in our direction, or that are in active binary systems, where they are accreting material from a companion star. The detected neutron star population is a small and possibly biased sample of the total. Black holes are harder still to count. Stellar mass black holes, those formed in supernova collapses, are thought to number in the tens of millions in the Milky Way, but we can only observe them when they happen to be in binary systems and actively pulling material from a companion star. In that configuration, the infalling material heats up to extreme temperatures as it spirals inward, emitting powerful X-rays that betray the black hole's presence. About 24 stellar mass black holes in such systems have been confirmed. The rest are invisible, drifting silently through the galaxy, identifiable only if they happen to pass between us and a background star and distort its light. Then there are the supermassive black holes, an entirely different class, found at the centers of galaxies and ranging in mass from about 1 million to tens of billions of solar masses. Sagittarius. A star at the center of our galaxy is a relatively modest 4.3 million solar masses. The black hole at the center of the giant elliptical galaxy M87, imaged in 2019 by the Event Horizon Telescope in the first direct image of a black hole ever obtained, contains approximately 6.5 billion solar masses. These objects are not formed by a single stellar collapse. Their formation history remains an active area of research, involving both the direct collapse of enormous gas clouds in the early universe and the accretion of matter over cosmic time. They are too large to be the direct descendants of ordinary stellar evolution, and understanding how they grew to their current masses is one of the central open questions in galaxy formation science. The influence of supermassive black holes on the galaxies they inhabit is not merely gravitational. When they are actively accreting, when enough gas and dust is funneling inward, they produce outflows and jets of extraordinary energy that can push gas out of the galaxy entirely, quenching star formation across regions spanning hundreds of thousands of light years. The process is called AGN feedback, where AGN stands for active galactic nucleus, and it appears to be one of the primary mechanisms that determines which galaxies stop making stars and go dark. The supermassive dead objects at the center of galaxies are, in this sense, the governors of galactic evolution, capable of both nurturing star formation in the earlier universe, when they compressed gas clouds through their gravitational influence, and suppressing it later, when their energy output became large enough to heat and expel the fuel for new stars. The stellar graveyard extends all the way to the center of every galaxy, and its largest occupants have shaped the universe's overall structure in ways we are only beginning to piece together. The stellar graveyard is not merely a collection of cosmic curiosities. Dead stars have been among the most productive laboratories for fundamental physics that exist anywhere in the universe, and discoveries made in the past decade have repeatedly opened new windows on old questions. The detection of GW 170817 in 2017 demonstrated that neutron star mergers are the dominant source of R process elements, which means that a significant fraction of the periodic table was made in the collisions of dead stars and distributed across galaxies billions of years before our solar system formed. The gold, platinum, and heavy lanthanides are not products of supernova explosions from single stars. They are the byproducts of the most violent collisions between the densest objects that can have surfaces. Every atom of gold that has ever existed on Earth was forged in such a collision, over 4.5 billion years ago, before the solar nebula had even begun to condense. The 2019 imaging of M87's black hole by the Event Horizon Telescope, a planet-sized virtual telescope assembled by linking observatories across the globe using very long baseline interferometry, provided the first direct visual confirmation that the shadow predicted by general relativity at the event horizon boundary actually exists. The image, released in April 2019, showed a bright ring of emission from superheated gas in the accretion disk, with a dark central region corresponding to the photon sphere and shadow of the black hole. A follow-up image of Sagittarius, a star, was released in 2022. Both matched the predictions of general relativity in their structure, providing yet another confirmation of a century-old theory at one of its most extreme applicable regimes. The Sagittarius, a star image was technically harder to produce than the M87 one, despite the black hole being much closer, because Sagittarius A star is far less massive, and its accretion environment changes on timescales of minutes. The team essentially had to image a moving target and average many observations to reconstruct a coherent picture. The measurement of neutron star properties from gravitational wave signals has constrained the equation of state of ultra-dense matter in ways that no terrestrial experiment could match. The tidal deformation of the two neutron stars in the moments before the GW17-0817 merger, the way their shapes changed as each one's gravity distorted the other, was measurable in the gravitational wave signal and placed limits on how stiff or compressible the matter inside a neutron star is, ruling out some theoretical models and constraining others. Future observations of more neutron star mergers with upgraded gravitational wave detectors will sharpen these constraints further. White dwarfs have served as precise cosmological clocks. Because they cool at predictable rates, the population of white dwarfs in a star cluster, their range of temperatures and luminosities, encodes the age of that cluster with a precision that complements other methods. The coolest, dimmest white dwarfs represent stars that formed the longest ago, and their temperatures set a lower bound on the cluster's age. When the Hubble Space Telescope directly observed white dwarfs in the globular cluster M4 in 2002, the data confirmed that the oldest stars in our galaxy are at least 12.7 billion years old, consistent with the universe being about 13.8 billion years old, and the first stars having formed within about 1 billion years of the Big Bang. Black holes, for all that we cannot see inside them, have become central players in observational astronomy through the phenomenon of tidal disruption events. When a star wanders too close to a supermassive black hole, close enough that the tidal forces exceed the star's own self-gravity, the star is torn apart and part of its material forms an accretion disk around the hole, producing a transient flare of radiation that can outshine an entire galaxy for months or years. These events are detected in large sky surveys at a rate of roughly 1 per galaxy per 100,000 years. They provide some of the cleanest evidence for the existence of otherwise dormant, inactive black holes. The ones not surrounded by continuously accreting gas. Most of the supermassive black holes in the universe are in this quiet state. Tidal disruption events are the only way to directly see them announce themselves. Fast radio bursts represent another dead star story that is still being written. These are extraordinarily brief, extraordinarily intense pulses of radio waves that arrive from cosmological distances, some from billions of light years away, lasting just milliseconds, and yet carrying more energy than the sun produces in days. Their origin was a mystery for a decade after the first one was discovered in 2007. The leading current explanation is that at least some of them are produced by magnetars, specifically by the powerful bursts of electromagnetic radiation that accompany starquakes in young, active magnetars. This was strongly supported in 2020 when a fast radio burst was detected from SGR 1935 +2 154, a known magnetar in our own galaxy, just 30,000 light-years away. It was the first time a fast radio burst had been convincingly linked to a specific known object, and the object was a dead star, the leftover core of a massive star that exploded perhaps tens of thousands of years ago. The most energetic flashes of radio waves in the universe, visible across billions of light-years, appear to be produced by objects we can also study in our own backyard. The pulsar timing array programs with networks of extremely well-characterized millisecond pulsars monitored by radio telescopes over years and decades have, in recent years, produced one of the most significant results in gravitational wave astronomy. Because millisecond pulsars are such stable clocks, any systematic variations in their timing across the network can in principle be attributed to gravitational waves passing through the galaxy. In 2023, multiple pulsar timing array collaborations simultaneously announced evidence for a gravitational wave background. A low-frequency hum of gravitational radiation permeating the universe, thought to be the combined signal from millions of pairs of supermassive black holes in distant galaxies, all slowly spiraling inward and producing gravitational waves simultaneously. This background had been predicted for decades, but detecting it required watching pulsars for over 15 years. Dead stars, the millisecond pulsars, served as the detectors, and what they were detecting was the gravitational noise produced by the most massive dead objects in the universe. Supermassive black holes, billions of them, scattered across the cosmos. The journey through the stellar graveyard is, in a sense, a journey through the layers of our understanding of matter and space-time. Each class of dead star represents physics pushed to a new extreme, and at each extreme, the theories that describe everyday reality either strain or break entirely. White dwarfs sit at the regime of quantum degeneracy, where quantum mechanics overrides classical thermodynamics and the behavior of matter is governed by the statistical properties of electrons, rather than their thermal motion. This is exotic but well understood physics, the same physics that underlies the behavior of semiconductors in every electronic device you have ever used, just taken to much greater extremes of density. Neutron stars push into the regime where nuclear physics and general relativity are both required simultaneously. The crust can be described using known nuclear physics, but the deep interior, where densities exceed those inside atomic nuclei, requires extrapolation beyond the regimes where our theories have been tested. The question of whether quarks are free in the inner core, whether some form of color superconductivity exists there, whether entirely new phases of matter arise at these densities. These are genuinely open questions in fundamental physics that cannot currently be resolved by any experiment on Earth. Neutron stars are the universe's answer to an experiment we cannot perform ourselves. The NASA telescope on the International Space Station has been producing some of the most precise measurements ever made of neutron star sizes, using X-ray observations of hotspots on neutron star surfaces as they rotate to constrain the radius. In 2019 and 2021, NASA published radius measurements of 2 neutron stars that, combined with the gravitational wave tidal deformability measurements from GW170817, began to paint a picture consistent with certain equation of state models and inconsistent with others. The interior is not, as some models suggested, composed of purely soft hadronic matter. It appears to be relatively stiff. The neutrons resist compression more than the simplest models predict. which rules out the existence of large hyperonic cores in most neutron stars, at least in the mass range studied. The data is still accumulating. Black holes mark the boundary of known physics in a different, more fundamental way. The singularity is not merely an extreme state of matter. It is a point at which the concept of space-time, as defined by general relativity, ceases to have meaning. The information paradox signals that quantum mechanics and general relativity cannot both be correct, as stated when applied to the interior of a black hole. One or both must be modified. The theory that will resolve this conflict, quantum gravity, does not yet exist in a complete form. The most developed candidates are string theory and loop quantum gravity, and they make very different predictions about what physics looks like at the Planck scale, which is the regime of density and curvature near the singularity. In string theory, the dimensionless degrees of freedom of the string and the extra dimensions it requires lead to a different picture of the singularity than the point predicted by general relativity. In loop quantum gravity, space itself is quantized, made of discrete building blocks, and the singularity is replaced by a high-density but finite region where the quantum geometry of space produces an effective repulsive pressure that prevents infinite compression. Neither theory has yet produced a prediction that has been confirmed by any observation. Black holes are the places where such a confirmation might eventually come from, not from observations inside them, but from the subtle properties of Hawking radiation, from the gravitational wave signatures of extreme mass ratio in spirals observed by future space-based detectors, or from subtle correlations in the properties of black hole mergers that encode something about the quantum structure of the event horizon. There is also the firewall controversy, which erupted in theoretical physics in 2012 when a team of physicists led by Ahmed Almheri argued that the three assumptions that had underpinned the conventional understanding of black holes — general relativity works at the event horizon, quantum mechanics preserves information, and faraway observers can trust the equivalence principle — cannot all simultaneously be true. At least one of them must be wrong. The resolution requires something dramatic. Either the infalling observer does not pass smoothly through the horizon as general relativity predicts, but instead encounters a wall of high-energy radiation at the boundary, like a firewall, or information escapes the black hole through some mechanism not captured by conventional semi-classical physics, or the equivalence principle breaks down in a way that has never been detected. This debate has driven significant progress in understanding the relationships between quantum information theory, gravity, and black hole physics, and it has not been fully resolved. The answers that come about the interior of neutron stars, about the resolution of the information paradox, about the behavior of matter at densities beyond nuclear physics, will not be footnotes in a completed picture. They will rewrite the picture entirely. The study of dead stars is not a finished discipline. It is among the most active areas of astrophysics and fundamental physics, and the past decade has seen more major discoveries than any comparable period before it. Gravitational wave astronomy, born with the first detection of merging black holes by LIGO in 2015, has already catalogued dozens of compact binary mergers, pairs of neutron stars, pairs of black holes, and mixed pairs. Each detection provides a new data point on the population statistics of these objects: how many there are, how they form, what masses they come in, how they are distributed through the galaxy. The upgraded LIGO and Virgo detectors, along with the new Kagra detector in Japan and the planned Einstein telescope in Europe, will detect hundreds of mergers per year in the coming decades, transforming what has been an occasional discovery into a statistical dataset. Among the most anticipated results are detections of black holes in the mass gap, a range of masses between roughly 3 and 5 solar masses where almost nothing has been detected yet. Whether this gap is real or a consequence of observational limitations may have profound implications for understanding which stellar explosions produce neutron stars and which produce black holes. The space-based gravitational wave detector, LISA, approved by the European Space Agency for a 2030s launch, will extend gravitational wave astronomy to much lower frequencies than ground-based detectors can access. At those frequencies, LISA will be sensitive to the slow in-spiral of stellar mass black holes into supermassive black holes. Events called extreme mass ratio in-spirals that will trace thousands of orbits before the final merger. The gravitational wave signal will encode exquisite detail about the space-time geometry of the supermassive black hole, providing precision tests of general relativity around spinning black holes at a level far beyond anything currently possible. The Event Horizon Telescope collaboration is continuing to refine its images and extend observations to additional targets. The science team is working toward movies of the dynamic environment near black hole accretion disks, capturing the plasma flows and jet launching mechanisms in real time. The Milky Way's own Sagittarius. A star has been observed producing flares whose origin is actively debated. Something is happening near the event horizon of our galaxy's central black hole on timescales of minutes to hours, and understanding that process requires linking what we know about general relativity with what we know about plasma physics in extreme magnetic fields. The next generation event. Horizon Telescope, a proposed expansion of the current array, aims to produce significantly sharper images by adding stations in space and at new ground locations. JWST's detection of the neutron star inside SN 1987. A has opened a new era in the study of young neutron stars. As the expanding debris of SN 1987A becomes more transparent over the coming decades, astronomers expect to see more and more of the young compact object inside it. If it turns out to be a pulsar, and the JWST data is consistent with a pulsar wind nebula around the object, then in 1987, A will give us a unique opportunity to study a neutron star from the moment of its birth, watching it evolve and spin down and cool in real time across decades, something that has never been possible with any other system. No other neutron star was born close enough and recently enough for this kind of longitudinal monitoring. The X-ray imaging and spectroscopy mission XRISM, launched by Japan in 2023, is producing the highest resolution X-ray spectra ever taken of neutron stars, accreting white dwarfs and the hot plasma around black holes. Its instruments resolve individual spectral lines with a precision that allows physicists to directly measure the velocities, temperatures, and densities of material in extreme environments, and to detect subtle signatures of general relativistic effects in gas swirling just outside the innermost stable orbit around accreting black holes. The Nancy Grace Roman Space Telescope, planned for the late 2020s, will conduct surveys of gravitational microlensing events expected to reveal hundreds of isolated, invisible black holes drifting through the galaxy, giving us for the first time a statistical census of the quiet majority of stellar mass black holes that produce no radiation whatsoever. Perhaps most importantly, the next few decades will see the maturing of multi-messenger astronomy. The coordinated use of gravitational waves, electromagnetic radiation across all wavelengths, and neutrinos to observe a single event from multiple angles simultaneously. The neutron star merger of 2017 showed what this approach can achieve. It confirmed the origin of heavy elements, tested general relativity, constrained the neutron star equation of state, and provided an independent measurement of the Hubble constant, all from a single event. Future core collapse supernovae within the Milky Way, which may occur within the next few centuries, would produce a burst of neutrinos detectable by the current generation of neutrino observatories, followed by gravitational waves and electromagnetic light across every wavelength. The last naked-eye supernova visible from Earth was in 1604. A comparable event today, observed with every instrument we have built since then, would be the most comprehensive study of stellar death ever conducted. Every major observatory in the world would pivot immediately. Every gravitational wave detector would run. The neutrino burst would arrive hours before the light, giving time to prepare. The stellar graveyard is expanding as the universe ages. Every star that ends its life adds to the population of these remnants. And with each new tool we develop, each new frequency of light or new medium of observation we learn to use, the picture we assemble of what those remnants actually are and what they do becomes more complete. We are still very early in understanding the most extreme objects the universe produces. If this kind of science, the deep physics of what the universe is actually made of and how its most extreme objects work, is something you want to keep exploring, subscribe to this channel. We cover the largest structures, the strangest objects, and the most fundamental questions in modern astrophysics. And there is a great deal more to come.